4 plus based phosphor, and it gives this narrowband red emission, and there is no infrared losses. And this is the current mid-power LEDs they use for lighting as well as mostly in displays. So many displays are now having this phosphor. But if you go for European 3 plus based materials, you can even create orangish or red-orange color, and then our LER increases. So the luminous efficacy increases because you can see this color more effectively than the red one. And if you want to increase the red parts, we can tune the European 3 plus peak by using different holes. So European ions can be very useful if we can use them for LED applications. And if you see the luminous efficacy of radiation, LER plot with color rendering plot with the nitride phosphorus, when we go for high CRI, high color rendering, our LER goes down. And with the KSF, it improves. But with our European 3 plus base materials, which we work on, we can get very good LER values for the same CRI values. And that's where we find the benefit of using these things. But then why people cannot use it? Where does it fails? Because we know that we need to have excitation in the blue part of the spectrum because LED emits in the blue, and that has to be absorbed by the phosphor. But many European 3 plus does not absorb there because they have FF transitions, and their CT band starts in the UV regions. In case of oxides, it's around 250 nanometers. In case of vanilates, the metal to the host absorption is around 300 nanometers. And if you change the anions to sulfides or nitrides, sulfides or other chalcogenides, you can change, you can tune the CT bands towards lower energy, but it's still around less than 400 nanometers. And also it becomes less efficient when you tune the CT bands towards this region. So European C plus has many problems. So the CT band and the host absorption bands are in the UV, so you cannot excite with the blue LEDs. We have limited options for coated phosphorus because then the donor material has to absorb in the blue part and it has to emit in the red, and then the emission spectrum depends on the donor material. The cerium and europium, which we can use as a sensitizer, they form a metal to metal charge transfer type reaction with this European 3 plus because they are redox pairs and they quench each other. The transition metals are not very good in this for europium using the blue excitation. And recently, GE Current has developed uranyl based complexes to get European 3 plus sensitization. This works well, but since it is based on uranium complexes, it's not very easy to export, and they have a lot of regulations to use them. So our solution is to use the Euro LED. So here what we do is we use nanoparticles. We use 1 nanoparticles to have a donor ion like cerium doped YAG, and we use the European another nanoparticles which is doped with the European based materials, and then we create a situation where energy transfer happens between 2 particles, and then we can excite 1 particle and get emission from the second particles. So in that way we can also control a lot of things. So how it looks, if we see that if we mix these nanoparticles in a conventional way, in not a nanoscale way, we can see that they look like that. And if we mix them in a nanoscale way, they can look like that. So the EDX is a more homogeneous mixture. And in the same scale, if you see, so we can see that if you don't mix in a nano-engineered way, you create a big chunks of the particles and they don't mix, and that's why they don't give energy, and you still get the green emission from the terbium when you excite terbium. But if you mix them in a very nice way, in a nano-engineered way, in a very nanoscale, like each particle is mixed with another particles, when you excite terbium, you get the emission from the europium, and that's how it looks. So that's how it works. And we can also tune the difference, the separation between the 2 particles, and depending on the separation, we can tune the color. So if you have a larger separation from the terbium and europium particles, you only get the green emission of terbium. And if you reduce the separation, you can get energy transfer, and the color changes from green to orange to red. And these are the particles we use for this application. And if you excite at 254, which is basically the CT band of europium, you get all 3 red emission. And if you excite 365, you get the different colors. And this is a special quality we can use for anti-counterfeiting. And that's our anti-counterfeiting solutions for the customers. So we use this IPA technology to make this kind of color changes, and it's very difficult to understand or reverse engineer, because you can see the XRD is quite same, and they only differ in the spacing between the particles, which is basically around 1 nanometer, which is very difficult to catch from the outside party. So you can make them, but it's difficult to reverse engineer. And this is how our phosphor looks, and these are the commercial banknotes. For the lighting application, it's a bit more challenging, because there we have to use cerium 3 plus as a donor. And then when you use cerium 3 plus donor and europium 3 plus as an emitter, when they come close, they quench each other, because they form a redox pair of cerium 4 plus, europium 2 plus. And if you excite cerium here, you can see that it can just go to the another state which is created by this redox pair, and then it comes down non-additively. And that's why we cannot see any emission when we make a material doped with cerium and europium. But if you make them separate enough, then your energy barrier becomes higher, and then the quenching doesn't happen, and then we can start getting brighter and brighter emissions. So that's how we tune the nanoparticles separation, and then we can create this europium emission based on cerium absorption. So here we excite at 450, and we can create the broad cerium emission and this narrow line of europium. So this narrow lines of europium is in the garnet host, but we can also change the host depending on what we need. So this is the theoretical things we want to achieve. So we want to achieve this kind of strong red emission with a pure color, and then we can get a color point changing from non-black body to the black body point. These kind of things. And this is our recent or last year's results, where we can create warm white LEDs using our IPET phosphor. And this is our another phosphor of europium 3 plus material, which can also give a nice red emission. And we are also developing more materials to go near the ideal case of the iridate phosphor for lighting application. So another point is for lighting applications, we need the high efficiency, like 90% efficiency of the phosphors. The nanoparticles are known to have less efficiency. And if you see, this is the literature plot for the nano-YAG. So when the nanoparticles are less than about 1 micron, the quantum efficiency is lower. At CIBRO, we could increase this efficiency of as many particles till 80%, even at the 10 nanometer particles. And we do some special treatment for these particles to get the almost 90 plus quantum yield of these particles. So this is quite impressive results from our side, because people were not or people were skeptical about nanoparticles used for lighting, but then we could show them that they can be as stable as the bulk particles. And these are the very small particles. This is the another particles we can make. So we can make a range of particles from 10 nanometers to a micron or something. So in conclusion, we have this Euro LED technology where we can use it to excite europium 3 plus via blue LEDs, and we can create the white lights. Also, we can use it for another applications like security inks and anti-counterfeiting. And our crystallite thing is the nano-YAG or nanoparticles of cerium doped garnet, where we can offer the nanoparticles for micro LEDs and other applications with a high efficiency and very small size. This is our team, and we also collaborate with different universities like UTEC University, MOLF, as well as companies like Current Chemicals, Luminous, and Momentum Capital is our investors. Yeah. Thanks.
Very thankful to the Dr. Atul. I am very impressed with your short talk. You talk about introduction with the personal and professional, then how you work on which technology, then basic to the application. Meanwhile, you talk about some mechanism as well. So it was like it was very beneficial talk to the students, to the professors who are joined today, and I guess it's very intellectual and informative as well. So with this, I would like to open the floor for the question and answer. And if you have any queries, students, professors, please go ahead. If you have any question, please. Is there any question to Dr. Atul?
Respected sir,
Yeah, please, Arvind.
very effective presentation. I want to know that if we try to make nanomaterials from two materials and we want to mix them, so which physical and chemical properties are more important when we are choosing our materials?
Yes, in terms here, what we are more interested is we want a material where we can get a good absorptions in the blue region. So we are actually bound with cerium doped YAG because that's one of the best materials we can use. And in a nanoscale, we want them to be small enough so that they can have this non-radiative Coulombic interactions. So Coulombic interaction happens around 3 to 4 nanometers is the maximum we can go. So we are looking for particles around 20 nanometers because then you can come to another particle close enough to another particles where energy transfer interactions can happen very effectively. So the particle size is more important. Also, your properties of ions is important. Also, in case of emitter materials, since Europium 3 plus or any rare earth ions, or mostly the Europium 3 plus is very sensitive to the host lattice. So we want to find a host material where Europium 3 plus can give a more pure red light, like strong red emission, weak infrared emission, and weak orange emission. And then it is also it has a good lattice that can work well with YAG because we also need to go for post processing. So the particle size and their stability and is also very important. So the first thing is the best spectral properties, and then the particle size and the stability.
Thank you, sir.
Sir, I would like to ask you something regarding you talk about nano engineering materials.
Yeah.
So, which methods exactly you use for that, and what are the ideal conditions to make the nano engineering material?
Yes, so nano engineering is a mixing mechanism we use. So mixing is not very difficult one, but the material itself is a quite special. We want nanoparticles, but we want nanoparticles which can form a colloidal solution, or which can form individual nanoparticles. Like in the literature, we can see that many people report nanoparticles, but they are aggregated particles, or they are attached. They have nanoscale dimensions, but they are not separate. So we want particles which are separate, and for that we use autoclave, like solvothermosynthesis. So you use a pressure cooker and you cook the reactants in the pressure cooker, and then you create a condition where the nucleation starts, and then the particle starts to grow, and then every particle is of same size, and then you can create them separate with each other. Normal or combustion method can also give nanoparticles, but then they are attached because you need to go for the post sintering, and that doesn't give you the proper properties.
Yeah. So, did you face the problem of agglomeration, and how did you overcome for that?
Yeah, so we make YAG nanoparticles using autoclave. So it's a kind of a special mechanism where you can create separate particles. And then we need to post treat it because the as-made particles are crystalline plus amorphous. So we then bake them, or we then heat treat them in a protective matrix. Like you put these particles in salt matrix, or you coat with a lot of silica, and then you bake it, and then you take out the silica out of that. So that's how you heat treat at high temperature so that they become more efficient, and then you remove the matrix so that particles again are separated.
Yeah. Okay. Okay. One last question from my end. you talk about the generation of lights, like right from the CFL, LEDs, and OLEDs, and all. What will be the future of the lighting industry? You think, according to
Yeah. Yeah, I think LED is still taking over. It's not completely transition, because I think in many Western countries, even in Japan, when I was in Japan in 2014, the Nobel Prize was given to the Shuji Nakamura and
Nakamura?
the team. That time, the Japanese government made it compulsory for every government office to change their lamps from normal lamps to the LED lamps. Also, we have seen that in Europe last year there was the mercury ban happened. So mercury ban means no more CFL and fluorescent tubes. So that happened here. But I think in many countries still it's not banned. So it will take over. It will take some time for LED lighting. For me, I think the super LEDs and the laser diode based lighting will be the future, but there are some regulations about laser safety and other things, so that will take some time. But that's where we can get more compact and more efficient lightings for especially for high fluence large area lighting applications.
So, any question from others, students? So, if not, Shruti, I would like to thank you.
Sir, excuse me, sir.
Yeah, please go ahead.
Sir, somewhere I learned that direct sunlight can be used as a tube lights.
Yeah, means I think it's not the solution we can offer for all times. You can use them in a highly lit areas where you can use this special reflectors or special diffusers to bring the sunlight from outdoor to indoor. But it's not applicable for the countries where you don't have sunlight or in the evening times, night times. Of course, sunlight is the best light. It has all wavelengths you need, uh, but it's not the available all time.
Okay, thank you, sir.
Yeah, anything, one? Anyone? Anything else?
Okay,
No.
so considering there is no questions at all, first of all, I would like to thank you to Dr. Shinde for your time and being here. It was really a very interactive session.
Welcome.
Thank you
Thank
so
you.
much, sir, for your valuable time. And of course, I would also extend my heartfelt thanks to Dr. Atul, sir, for his very interactive and very knowledgeable, illuminating session for all of us. Thank you, Atul, sir. And finally, I like to thank all the participants who joined us and enjoyed this session. Thank you. Thank you, one and all.
Yeah, thanks, Shruti.
Thank you. Thank you. Thank you, sir. So, with all permission, I'm ending this session here.
Yeah,
Thank you.
thanks to Nilesh as well.
Have a good day.
Yeah, thanks.
Okay, sir. I will convey.
Yeah,
Thank you.
thank you. Thank you.
एक्सेल फाइल
लैपटॉप नहीं होगा, लैपटॉप नहीं है ना।
अच्छा या
Please do.
let me see.
Please do. ठीक है, चलेगा। मैं फिर पूरा बड़ा वाला है उसमें से 2 मिनट में से कर दूँ यार। हाँ। हाँ, हाँ। मैंने वो मैडम को बोला था बख्शीश हुआ है ना।
कॉलर नहीं कर लैब में देना है क्यों नहीं
स्क्रीनशॉट भेजा है और बायोडाटा भी भेज रही हूँ, उसमें से कुछ रहा तो 4 पॉइंट आप वहां से भी लीजिएगा। अभी आती हूँ मैं, मेरे से थोड़ा टाइम लगता है यहाँ से। ठीक है। हाँ हाँ, अभी आपको आया नहीं, ये देखो ना, मैंने भेजा हुआ है। वो है, दिख तो रहा है ना। ये देखो नीचे देखो, मैंने ये भी भेजा है तुमको, उसका सेकंड पेज ले लेना सारे। ये कौन सा है, दिख रहा है। ऐसा करोगे, दिखती तो पढ़ने में प्रॉब्लम है ना कंटिन्यू, तो कैसे करोगे ऐसे। मैंने आया है, आया ये बात आना चाहिए। ये देखो ये वाला बैड, अरे ये कौन सा तुम्हारा है। नहीं एसपी तुम्हारे मैंने यार, तुमको कब शेड्यूल मिला कि नहीं ना। अच्छा ये दूसरा नाम, नहीं नहीं ये इस पे नहीं देखना, जैसे मैंने कहा उस पे नहीं आ रहा तुम्हारे को, उस पे नेटवर्क का प्रॉब्लम है तुम्हारे 30 years experience, 672 people, 4 research स्टूडेंट, ठीक है, 2 पेटेंट हो गया। अभी कॉलेज में रहेंगे, एक मिनट रुको ना, और मैं देख सेकंड ये देखो, ये पहला नहीं, मैं तुमको दूसरा वाला, ये वाला देखो, यहाँ जा तो रिसर्च में कितना देर चाहिए आपको, यहाँ से ले जाएगा ना, रुको ना, आई कैन मैनेज अभी, ऐसा है, कैन वर्क। स्क्रीनशॉट दिया मैंने अभी, इसमें मैक्सिमम अचीवमेंट्स किसी के भेजे, मैम इस पे अभी भेजा मुझे शीट्स मिलनी चाहिए। दिस सेशन सर, एक बात बताइए ना, अभी कौन सा सेशन स्टार्ट हो रहा है? अच्छा सर, और कितने लोग हैं स्पीकर ऑफलाइन में? ऑनलाइन हाँ, मेरे साथ में एक मौका है, फॉर्मेलिटीज है तो करना तो पड़ेंगी। यहाँ है स्टार्ट से हाँ, दोनों ही है।
नाही तू म्हणाला अरे आइए रोहिलो कोण करत आहे काही नाही बस
A very good morning to everyone. After reviewing this session, we had secretary of MSS, Dr. Vikas. We are all pleased here to see all unemployment. So let's start our invited speaker session. So for the session we have two section chair, one section chair Dr. Shruti Patel and co-section chair Dr. Zoya Rao. So first of all, I would like to read their invited. Dr. Shruti Patel is presently working as an assistant professor in University College of Engineering. She has a rich experience. In 16 years of tenure, she has pursued masters and doctorate degree from RMIT University. Also, she has obtained her bachelor's degree in education from SCT University Mumbai and MPhil degree in physics from Global Open University Nagaland. She has 2 copyrights on her name and 1 patent from each. She is also So let us hope that Free University Nagpur achievements are first from the group of others in various national and international levels and painting as well as a confidence on her writing. Her research areas include non-linear optical materials, synthesis materials, and semi-organic optical materials. Presently, she is guiding more research students for a PhD. She is associated with various professional bodies such as Indian Association of Acoustic Growth, IACG, Indian Association of Acoustic Teacher, IATD, International Association of the Engineering, IAE, and Indian Society for Training and Development, ISTD. She is reviewer of various international journals of the engineering research and technology and international journal of the emerging fields in engineering and basic sciences. She was actively involved in organizing various national as well as international conference seminars. We are very thankful to you, ma'am, as you are here as session chair. I request all the participants and the parents here to kindly applaud for them. Our next session co-chair is Dr. Kavita Gaur. Kavita Gaur is also a professor in Priyadarshini College of Engineering. She has 30 years of experience. She has published 72 research papers in the journals. 2 patents are granted here, and she has written 12 books. The first PhD students were awarded by her. She has received Best Research Paper awards. She has presented paper in India as well as in international conferences. She has organized the conferences where she was appointed as a convener. So we are very blessed to have Dr. Kavita Gaur with us. Kindly applaud for us. Now I hand over the mic to Dr. Kavita Gaur for proceeding. Good afternoon. Good morning, ladies and gentlemen. We are going to start the international conference material science was March 24. So our speaker is Dr. Champagne K. Associate Professor and Director, Scientific Institute, Kannur University, Kerala. Sir had 14 years of teaching experience and completed PhD in optoelectronics from University of Kerala in 2010. He has completed many projects funded by University Grant Commission and Government of Kerala. Sir has published 52 research papers and received award of Best Presentation. He is working as a reviewer for reputed journals like APL, ACS, Elsewhere, and Springers. Sir, I invite to deliver your talk.
It's okay. Yeah. Thank you. Good morning, all. Myself, Dr. Nisamuddin from Kannur University. My topic of presentation is perovskite nanophosphor for latent multifunctional applications. Okay. Okay, sorry for the disturbance. Then myself, Dr. Nisamuddin from Kannur University. Before start my talk, then let me introduce our institute. This Kannur University it is located in the north Kerala. It is established in 1996. We have 26 departments and more than 200 affiliated colleges. Next, please. Then Department of Physics. Actually, Department of Physics offers so many programs, including then Master, MSc Physics, then Specialization in Advanced Materials, then MSc Nanoscience and Nanotechnology. Actually, it is joined with another university, that is the first initiative in India. It is inter-university program, that is collaborates with another university of Kerala, that means MG University, Kottayam. Then PhD in specialization in film technology, nuclear and particle physics, nanomaterials, etc. Then recently we have started then 5-year integrated master programs also. Then we have some research facilities. Microraman spectrometer, actually it is imported from Oriba, France. And UV visible spectrophotometer JASCO. Then spectrophotometer is imported from Oriba, USA. Solar simulator and X-ray diffraction spectrometer, it is Alga Japan. And also some preparation techniques and high vacuum coatings, spray pyrolysis unit, dip coating and dip coating unit is also. Okay, then let me start our core research topic. Then development of lighting technology. You know, the light is very important for us. Then the history of light in 1879, then we are using then Edison's light bulb. Then after in 2021, then single layer perovskite phosphor we invented. Yes, that's it. Okay. Are you seeing the okay. Then the type of luminescence. Then luminescence is classified with depends upon the excitation source, that means photoluminescence, electroluminescence, chemiluminescence, then cathodoluminescence, radioluminescence, and X-ray luminescence, and also mechanoluminescence, bioluminescence, thermoluminescence, and piezoluminescence, etc. There is a photoluminescence, the excitation source is light, and for electroluminescence, in its excitation source is electric field. Then chemiluminescence is the chemical reaction, and cathodoluminescence is the electron beam. Then radioluminescence in X-ray or something like. Then mechanoluminescence actually is a turboluminescence. Then bioluminescence and so on. Then photoluminescence is mainly classified into two. Then fluorescence and phosphorescence. Actually, the process is happen spin allowed transitions. That means transition from singles to ground state. Then lifetime of order of the nanoseconds disappears when source's excitation is removed. For the case of phosphorescence, actually spin forward transitions. Yeah, the transition from excited singlet to ground state via triple state. Then lifetime of order of microseconds to several and or drop. Okay. This is a mechanism of fluorescence and phosphorescence. Actually, it is a familiar diagram. Then excitation mechanism. Then we have two type of excitation mechanism. That means one is direct, and the first one is the direct, and this is the second one. Because for the luminescence materials, we have activator and host. Sometimes is host is directly absorb the energy sources and it is excited. Then sometimes then host is absorb the excited energy, or host or sensitizer is absorb the energy and transfer to the activator. This both are mechanism of the excitation mechanism for luminescence activities. Then up conversion and down conversions actually is a basic, so we will skip this. Then light emitting diodes. Then main source of our main aim of our research is build a better light emitting diodes. Then we know the light emitting diodes. Then currently we are using the light emitting diodes are the main sources of light. Then instead of fluorescence lamp and incandescent lamp, then we are replacing the conventional light sources. Yes. Then three type of white LED mechanism is there. The first one is color mixing. That means first actually it's not color mixing. Actually it's a blue emitting diode with cotton with the yellow phosphor. This is one type of producing white light. Next. The second one is color mixing. That means we combined three colors. That means yellow, green, and then blue, green, and red, and mix it to produce a white color. And last one is a single. This is our main focus area because a single phosphor produce white light. That means then we are using an excited source as a then we are coating. Then we purchase UV LEDs from the market and coating a single phosphor. Then it produce a white light. That means a single phosphor produce a white light. That means it is combined. That means they have three excitations. That means but this one then we put three LEDs separately. That means blue LED, then green LED, and red LED. But in this case, then it's a single phosphor emit three emission. That means blue, green, and red. Then currently we are focusing, almost all researchers are focusing this type of phosphor. Yeah. Then this is method of attaining actually elaborate itself. Then for the previous slide. Then actually then NUV chip with the white phosphor. This is our main theme of focus. Then displays also. Then another important applications of phosphor is display purposes. Okay. Then this is a quantum dot, and we are also in our lab is producing. This. Then our lab is mainly preparing the double performance materials. And I think yesterday some speakers are deeply discussing about the perovskite and double perovskite materials. So it's a repetition, so that can be wish to skip this section also. Then rare, actually it's a rare, these are vitamins of modern industries. Then this is the main rare elements we are using in our laboratory for preparing the nano phosphor. This is and this also. Then for this talk, we are focusing on the three materials, that is LMG, YMG, and GMG. This is a code name LMG, YMG, and GMG, that is La2MgGaO6 and Y2MgGaO6. And this GD2MgGaO6 is dot with the dysprosium. Okay, then they are emit, then 480 nanometer, then 574 nanometer, and 680 nanometer. Then actually this YMG, LMG, and GMG docked with the dysprosium, which is emit three colors simultaneously. Yeah, then synthesis preparation. Then we have many techniques for preparing these phosphor materials. First one is on-state method and for precipitation method, molten salt assisted method, and combustion methods. Then each and every method have its own limit and its own advantages. Then I listed the advantages of peculiarity of these methods, and we are focusing the combustion method. Then currently our lab is preparing the materials on this method, that is low. So advantage of it is low temperature, redox, upset exothermic reactions, less time, small crystalline size, high melting point, homogeneity, constant nitrate, and then pH maintenance. It's energy savings because we are currently using the combustion method. We can get a very good quality product. Then prepare the perovskite nanophosphate, then especially for LMD, GMD, and YMD methods. Then mainly by solid state method and partially combustion method. Then we are trying for both methods. Then doping with the iron BY ions. Then optimizing selective best synthesis method and finally co-doping. Co-doping, and that means cis excitase, the linear strontium samarium. Then mainly applications is anti-counterfeiting, encryptions, and vital UEs and latent fingerprints. Then photoluminescence emission spectrum of LMG. Then as we are already discussing, then we have three emission speeds. That means around in between is for 160 or for something. Then excitation wavelength is 351. Then that means it is blue, it is green, it is red. Okay, this is the main highlight of our phosphor materials. And we can get a three color for a single excitation. This is see the color chromaticity diagram. Then this is actually then this is prepared by us. That means we are purchasing an ultraviolet LED from the market and put in our prepared laser, and you can get a very bright white light. Just actually it's not a commercialization or factory made. It's simply then put our phosphor and they can get. Then also the GMP is also very we got. Then I got 480 nanometer and 577 nanometer and 671 nanometer. Then this is our color for this. And this is also comparison. Then for ideal library, then this GDMT, that means, and actually GDMT means it is stopped with the disposal, that means the not name. Then comparing these samples for ideal library, XY is 0.333 and 0.333 north, And the CCT value is about 4,500 to 6,500. CRI is that. So, but in our sample, we can approximately, that means 0.3224 and 0.3247. That means then we are reaching towards the ideal line. That means it is almost there, and this also. And CCT is not important, but because we are in close to then 6,500 K, it means a cool light, and 4,500 is a warm light, Then we got nearly cool white light, and CRO value is actually the 100 is an ideal value, it's equal to sunlight, but then we got 86 and 87 for then color purity is also, then ideal color purity is 0, but in our case, we up to 4.5, then we can try to reduce the value to 0 or something. Then photoluminescence spectrum of then again show the YMT for different wavelength. That means this is excitation for 353 nanometer, and okay, we got this. This is also YDMT color purity as shown there is like yeah. Actually, this photoluminescence emission. This is a preferred sample. Okay, it is for a daylight. When we excite it using an ultraviolet LED or ultraviolet, then we are using the LED. We show some LED lights. We got a white. Maybe this color. Yeah. And also in for 18 nanometer, it's almost it's not a good white, but it's almost got a white color. Then actually this is a double excitation. It's a highlight for our anti-counterfeiting and security applications because the same phosphor emit both color for the excitation for UV and infrared emissions. Okay. Next one. Then this is our mainly focus applications. Then we will discuss one by one. Then this is our novel approach to design and barcode. Actually, we have already published this work. This is a method for pairing, or actually our main in our current topic presentation is security applications. Phosphor for security applications. This is used for security applications. Then, when we secure a product from the counterfeit, then we prepare a phosphor materials and coat on the product, on the box for the product. Then it's a combination is secret. We know the combination is secret. We can then applying on the product. Then during the sunlight, that's no emissions. But then if something doubt regarding the genuinity of the product, then we can use a particular wavelength source. Using the particular wavelength source, then illuminating it. If that particular wavelength of emissions is produced, especially for this material, then produce this emissions. Okay. Then for intensity recorder, we can collect the intensity as a width. Okay. Then this intensity, the height of this intensity as a width. Then converting this intensity is converting this width using the intensity. And using the software, we can convert printed barcode and refill. This is our prepared barcode, and it is also we are trying for its aging. Okay, then we are from 2026. May 2023 and October, then we got safe result. That means there is no degradations of our phosphor because we can use this phosphor for a long time. Okay. And it's also it's another competing applications. Then we are already discussing. Then we have one type of materials illuminating with two wavelength. That means UV and infrared. Then first we are then actually staying is color positive. Then illuminating with the UV light. Then we got a blue color. And UV then illuminating with an NIR, that is we got a red color. Okay, that means it's a high security. They normally in our security print, especially for count and not and count and another thing, currency not another things. We have only one phosphor materials illuminating the UV and it is drawn. Okay, but we can easily imitate it because it's a single excitation and single emissions. But these materials, it is double excitation and double emissions. It is give more security than using the current material. Okay, then. Sorry. This another this all samples and all experiment is done in our laboratory. To be visible for this writing, yeah. This is a fingerprint for different persons and different surfaces. That means there's 20-year older female, actually then 30-year older male, and etc. etc. Then in our current situations, we are using titanium dioxide or such type of powder for fingerprint variations. But its contrast is very less. Compared to it's like a foggy appearance. But using this powder, then we got very high contrast illuminations, and we got a recognition patterns. Then actually this shows the very high contrast pattern we can reproduce for use both UV and NIR light. This is one important applications of phosphor material for this dual emission phosphor materials. Yes. And this is summary of my work. Actually, we are preparing for three type of materials. Then it's mainly applications for barcode. Then YNT. Actually, it's a lithium as a sensitive. Dysprosium is that carbon. It's an activator. Scale intensity, crystal splitting, and contrast. Then mainly an applications is then LA, that means YNT is mainly used as a barcode and GLT is for anti-counterfeiting and fingerprint visualizations, and actually LFG is for a white light LED applications. Okay, thank you. This is my name of researcher, and thank you. Any doubt?
Hello.
Yes.
Hello. Now session is open for question and answers. If you have any doubt, ask. Thank you so much, sir. But I have a question.
Yes.
Nowadays, we are using barcode in mark sheet. As I have seen that, I know some idea of it. We are using hospitals and many more things. Could you explain the barcode which we are using in mark sheet? Is the same whatever you have told me?
Yes. Actually, the currently from barcode where we can easily imitate it. But this type of barcodes, then for a dialect, we cannot see anything.
Yes, which will different.
Yeah, you can imitate. But using a particular light, we can eliminate.
Yes.
Then nothing, but we are
Identical.
using a detector, we can collect radiant energy, that means luminescent material. This intensity is converted into width of the bar. Okay, that's more sectoral.
Yeah.
But for for examination paper, I think it's not necessary. This type of securities, higher,
Higher side.
yeah, higher materials and high costly items.
So are you using this thing with the government, central government and all that?
Actually, it's a constructed and actually it's working, but it is not commercialized. We are trying for
Commercialization. Thank you so much for nice enlightenment along with the Center for Advanced Research and Facilities, because without analysis we cannot go for research that is needed, and so many instruments are in such department. And thank you, sir. And now I have
Sir, it is possible to use a phosphor for different applications. Same phosphor for different applications. Yes, maybe depends, but it is depends upon the properties. So we can use, for example, for in the case of a PN junctions, we can use as a used as a normal PN junction, or used as a ion, etc. Like this, depends upon the manufacturing and processing conditions. We can use as. Okay. Then thank you, especially for yeah.
So regarding asking about the grouping phosphorus.
Yeah.
So in some of the paper, I seen that they were mentioned there is no possibility to transfer of energy from dy to other layers. And we got some papers where it is they have proven that dy is transferring energy to EU or TP. So which side is right? Whether it is possible that dy can transfer energy?
Transfer. Yeah. In our experience,
It's transfers.
yeah, transfer.
Thank you.
Then thank you for giving. Then the one thing, then our university has a very good instrumentation center facilities. Then anyone who want to use this facility, then we can go to our website and send some. I think it's a very less payment compared to all of the other instrumentation center. Then we are actually increasing the number of equipments. We are planning to more and more equipments. Thank you.
Thank you so much, sir. We are very grateful to receive this valuable knowledge from our keynote speaker, Dr. Nizamuddin, and we have got a very good opportunity to receive this knowledge from you, sir. So we acknowledge this by giving a memento and certificate. So please come.
Sophia,
Yes, right. Good morning to one and all. So let's move to another session, another talk of the session. So for this, first of all, I welcome Ramesh Sachdev sir and Dr. Pankaj Ramesh Sachdev sir. And we welcome you, sir, to Mars 2024. So with first permission, I'll look forward his brief introduction here. Sir has completed his bachelor's degree in 1999 from Nagpur University. After that, he did his master's from Pune University in 2001. For his doctoral work, he demonstrated the structure, origin, and importance of strain responsible for various electronic and magnetic phases observed in perovskite oxide from UGC DAE CSR Indore in the year 2007. Along with this, he worked as a research associate at UGC DAE CSR Indore in the year 2007 to 8. After completing PhD, Professor Sachdev joined Baba Atomic Research Center BA in 2008 as a scientist officer lead, where he set up the state-of-art coding facilities for optical and neutron mirror applications at BA and proudly published his first research paper. In June 2012, Professor Sachdev joined the Indian Institute of Technology IIT Indore as assistant professor. In IIT Indore, Professor Sachdev is involved in research, teaching, and established a material research laboratory which works on the physics of highly correlated electron system, quantum confinements, and then system and scientific instrumentation development. More than 100 research papers published by Sir. Professor Sachdev is having a strong hold on various important sample characterization technique and working as a rep for various scientific journals from AIP, IOP, elsewhere, MRS, Daily, Springer, etc. And currently, he is working as a professor at the Department of Physics, IIT Indore. With this wonderful biodata and introduction, I welcome and request Professor Sachdev to proceed with this talk. Yes, sir.
Thank you, madam. I hope I am audible to all of you. Am I audible to all of you over there?
Yes, sir.
Okay, thank you. Thank you, madam. So let me first thank the organizer for the invitation, and especially Professor Ugemuge and Professor Kale for their kind invitation and giving me opportunity to present my work in front of all of you. So basically, when I was discussing about this particular lecture with Professor Ugemuge, he said that the conference is basically being attended by most of the PhD students of various disciplines who are working in the field of material sciences. So I thought that I will basically give some glimpse of applications of optical absorption spectroscopy. There is some echo which is coming. Maybe the others can mute their mics. Others, please mute their mic. Okay, thank you. So, so the thing is that this lecture is basically for the young PhD students. That how you can basically use a very small, very economical experimental technique to do something which is really worth publishing. Okay, something which is really. I will not say we are doing great work, but which is really very much informative. Okay. So, you know that optical absorption spectroscopy is something which is really economical, which even a small college can afford to buy the optical absorption spectroscopy setup. Okay. And obviously, you need to tune some parameters for that particular spectrometer, and then you can really use it for the research purpose of your own in your own area. So basically, as I said, we will be discussing about the applications of optical absorption spectroscopy. So the plan of my talk will go as follows. First, I will discuss what is absorption in general. Then the semiconductor as we understand. Then how we can basically use optical absorption spectroscopy to basically characterize these semiconductors, and what wonder you can do. That's something which I will be explaining to all of you. So this is the hydrogen atom spectra, which is known to all of us. Okay, in 11th standard, we know that we basically look into various Lemon series, Baumol series, Paschen series, and all those series which we basically learn in for hydrogen atom in class 11th or 12th. Okay. So what happens is that whenever you have some particle in energy state E1, and and if you basically supply some energy to those particles, and if energy state E2 is available, then if you supply the sufficient energy to the particle on the energy state E1, then they can basically absorb that energy, and they can basically go to the excited state, which is energy state E2. Okay. In this case, what is the basic prerequisite? The energy of the incoming beam or incoming excitation source that must match or that must be higher than or equal to the energy difference between the states E1 and E2. So this is something which all of us are aware of, and that's what we basically see in hydrogen atom spectra when we basically study the same in our lab to see the hydrogen atom spectra. And then we basically look into various series. We verify the Bohr theory of hydrogen atom. That's what I know that most of us have already done. Okay. So absorption is essentially a phenomena where the energy of the incident excitation source is basically used to excite the particle from lower state to the higher state. Okay, and those particles may be electron, that may be molecule, that may be phonons, whatever it is. So this is in general we can basically discuss the absorption. Okay. Now let us come to something which is semiconductor material. Okay, so this is something all of us are familiar with. This is one of the this particular figure C is basically the metal where the valence band and the conduction band are overlap. The figure B is essentially the semiconductor, where there is a moderate difference between the energy difference between the valence band and the conduction band. And in the case of this insulator, this particular gap is very large, and is around or more than 6 electron volt. We call that these are the insulators. Okay, so this is something which we how we basically characterize metal, semiconductor, and insulator. Now, if you look into this particular energy band gap in a case of semiconductor, it varies, as I said, it's a moderate. It varies from maybe 0.5 electron volt up to close to 3 electron volt, something like that. Okay. So now if you look into the electromagnetic spectrum, and if you basically look into the energy of the visible radiation, then you will realize that you can basically use the visible light or some part of the soft UV or some part of the IR. If you now compare the energy of this particular part of the electromagnetic spectrum, to be precise, UV visible and IR, okay, then you will see that the band gap of the semiconductor, most of the semiconductor material also lies in the same region. So what does it mean? It means that I can basically excite the electron from valence band to conduction band, provided I have this particular spectrum which is available with me. Okay, UV visible and NIR, I can say. Okay. So as I said, if I basically shine an electromagnetic spectrum onto the semiconductor, if the and if the energy of this particular semiconductor material is equal to or higher than that of the this particular energy difference, then you can say that okay, one can excite the electron from valence band to the conduction band in a case of semiconductor material. Okay, so this is a very something which all of you will agree, and this is something which basically happens. So now what we can do is that we can, if you are intelligent, then you can really design some experiment. So what kind of experiment one can design is that you take an incident light, you take a light of some particular energy E, and then what you do that you basically measure the reflectance of that light. You just simply you measure the reflectivity of the light. Okay, you measure the intensity of this particular primary beam, and you measure the intensity of this particular reflected beam. So as you can understand that as as long as the energy of the incident beam is less than that of the band gap, then obviously that particular photon will not be absorbed, and that will be basically reflected back. Okay. So now if I basically perform the reflectivity as a function of energy, then you can see that, or wavelength, you can see that for higher wavelength means for lower energy, you can see that there is a significant amount of reflectivity, and as soon as the band gap of the means, or the energy of this particular incident radiation matches with that of the band gap, you see that there is a drastic change in the reflectivity, drastic decrease in the intensity or reflected intensity, and after that it goes to zero, really zero. So what does it mean? It means that the incident light is really absorbed to excite the electrons from valence band to conduction band, and at that particular energy you will see that the reflectivity of that particular radiation, that will basically vanishes. Okay. And this particular information you can use to extract the value of band gap in the case of semiconductor material. So what we have essentially done as of now, we have simply performed the reflectivity experiment as a function of wavelength or the energy of the incident radiation, and then you see that at what energy this particular reflectivity goes to zero, and then you basically apply some laws of physics using Kubel-Kamank modeling or tau plot type of analysis, and then you basically analyze the data to extract the value of band gap in case of semiconductor material. So what I just wanted to convey is that a simple reflectivity experiment using a light source which is present in this particular conference room can be basically used to find out the band gap of the material. Obviously, you have to basically perform the experiment intelligently, and you can basically do that. Okay. So what actually happens is that you have a source of a light, then you have some optical slits there, then you have something like a grating or a prism. Okay. Then you basically select a particular beam of a light, means particular energy of the light, and then you basically perform either transmission or reflection measurements. Okay. And this is also schematically shown in this particular spectrophotometer. So those who have spectrophotometer in their lab, so they have something which is a source of a light, which is most of the case a xenon light, xenon flash lamp, and then it basically produces the white light. Then you have the optical element over there, then you have a grating here, and then grating select a particular light which basically filters using some optical filters, and then you get a particular light on your sample, and then you perform basically the reflectivity or transmission or the absorption experiment. Okay. And then if you basically rotate this particular grating, then you basically choose a particular light, and then that's how you basically perform the basically the reflectivity measurements or the transmission measurement, whatever is of your interest. Okay. So what we have essentially learned is that as of now, using simple reflectivity experiment and some optical element as shown here, you can basically that particular setup can be used to find out the band gap of the material. Okay. So now, and this is some experimental data which I have shown for the common samples. Okay. So now let us see what further you can do beyond band gap. Okay. So now the thing is that when you talk about any material for that particular reason, not only semiconductor material, so you take any material, that particular material will always have some type of defects. Means you can have the vacancy, you can have interstitial impurity, you can have self-interstitial, you can have substitution impurity, you can have Frankel defects, you can have line defect, you can have dislocation, you can have twin boundary. So large number of defects you can have in your solid. Okay. Now, if you look into this particular figure very carefully, you will see that the point near to the defect, you will see that the regular arrangement is really slightly disturbed, and as a effect of that, what happens is that you see that there is a slight change in the value of lattice parameter near to the defect. Okay, a very slight change in the value of lattice parameter near to the defect. So now let us look into the interference of a Bragg wave in a lattice. You see that means for an electron, the de Broglie wavelength can be written as something like this. Okay, and then and those electrons having the de Broglie wavelength of the order of interplanar distance, they will basically backscatter. And what you can do is that you can basically write using these k is equal to n pi a sine theta, and then you basically write e is equal to k h cross square k square upon 2m basically, and you see basically you get this ek diagram for this any semiconductor material. So this particular ek diagram is really fine, no problem in here. But the thing is that when you have defect present into the lattice, as shown in the earlier slide, uh, you can have this A plus minus delta A present into the material. So as a result of that, here I can show A plus delta and A minus delta A. So as a result of that, if you are only A, assume that only, so then you see that EK diagram is very, very sharp. But if you have the variance in the value of lattice parameter due to something which is called defects present into the lattice, various defects, then you can see that there are some additional tail states are basically present. Means basically you can predict through this simple formula, E is equal to h cross square k square upon 2m, where k is equal to n pi sin theta, and then you put here a is not this particular is not unique, but it's variance. But most of the lattice parameter are basically will have the lattice parameter A, and very small number of unit cell will have lattice parameter A plus minus delta. So therefore this particular central line is very, very dark, and these particular tail states are basically the faint one. Okay, so these particular tail states are essentially called Urbach energy, okay, or width of the Urbach tail states. So what happens is that means assume that there is no impurity present into the sample. The sample is really very clean, no defect, ideal sample. So you can see that this is the very sharp conduction band and very sharp valence band. But as soon as you put something, then you will see that either due to potential fluctuation or due to variance in the value of lattice parameter, you will see that. So this is essentially the magnified view of this. So you can see the presence of Urbach tail state present in the sample, and this gives the information about the electronic disorder into the semiconductor material. Okay, so the information of this particular electronic disorder or the Urbach tail state is present at these in this particular region of the absorption spectra. And you can see that as you basically increase the disorder, this exponential decay, basically the decay rate, the rate of this particular decay will vary as a function of disorder. Okay, so if you increase the disorder, this will have basically this will drop with a lesser rate. Okay, so for a disorder-free system, this particular absorption is really very, very sharp. Okay. So earlier in the earlier example, what I have essentially shown that how you can basically use the optical absorption spectroscopy to find out the band gap. Now you can basically analyze this particular part of this particular absorption spectra, and you can basically look into the amount of disorder or electronic disorder, or what is the value of Urbach width of the Urbach tail state present into the sample. Okay, so now the thing is that you can not only find the band gap, but at the same time, what is the width of this particular Urbach tail state? That is something which you can basically estimate if you properly model this particular part of the absorption spectrum. Okay. Okay, so far so good. Now let us revisit this particular system, this particular defect level once again. So you can see that, okay, if I have some defect present into the system, then near to defect there is something which is called slightly changing the lattice parameter. Now, if you just recall your semiconductor physics, which you have discussed in +2, then you know that if you basically put phosphorus into the silicon, you have a free electron present into the system, and then you to keep this particular free electron, you basically add some level into the conduction band and valence band. It is called acceptor level or donor level. Okay, means depending on if you put aluminum here or phosphorus here. So for phosphorus it will be a donor level, and for aluminum it will be the acceptor level. So these are the levels which you basically shown in this particular energy diagram, and this is something which I know that all of you are aware of. Okay, now if you ask the question, can you get the information about these particular levels in using optical absorption spectroscopy, then the answer is obviously yes. And obviously you need to basically perform this optical absorption spectroscopy very intelligently. So here what I have shown is that this is the band gap you can measure. Here you have shown the Arbac energy. Now if you basically very cleverly basically analyze this part of the spectra, and I must tell you that you need to perform the differential optical absorption spectroscopy. Means you need to have two particular sample. One is the defect free sample and means ideal sample, and one with the some type of defects present in the sample, and you basically pass your reference beam through both these, basically through the ideal sample and the one beam through the other sample which is having some defect, and then you basically perform the differential spectroscopy. So then you basically get this type of signature into the optical absorption spectra, and this type of signature you can model using some density functional type of analysis. So this is actually I have shown the ZrO2 with having the oxygen vacancy and having the ZR vacancy. You can see that the peak of due to oxygen vacancy is around 2.5 electron volt, and the peak due to ZR vacancy is around 1 electron volt. So if you now, so this is the theoretical data, and this is your experimental data. So now if you look into this particular, which is close to 2.5 electron volt, you can see that your sample is having this type of oxygen vacancies into the so the thing is that the optical absorption spectroscopy, so you can see that this particular intensity is very small, okay, as compared to this. So if you look into these particular numbers and these numbers, so this is, so you have to really magnify, or you have to really perform your experiment very intelligently, so that you can really probe what kind of defects are present in your sample. Okay, so this is how you can basically find out the presence of the defect states. Okay, so just to summarize the whatever we have discussed as of now, the region 1, so you can basically write this particular optical absorption spectra into 3 regions. Region 1 to estimate the band gap, region 2 to estimate the Arbac state, and region 3 basically the lower energies basically region to estimate the presence of defect state which may or may not be present in your sample. Okay, so you can look into this particular paper for the detailed analysis. So now let us look into the phenomena, any basically interaction of the light with matter. So when you talk about the interaction of light with matter, you know that the total energy always conserved. So you have finite absorption, finite transmission, and finite reflection. So now you know that with a reflection and transmission, you basically estimate not only the value of band gap, Arbac energy, and the defect state, but you can also find the refractive index, because you know that the reflection coefficient is also proportional to the properties of that particular material. So here N2 is the refractive index of this particular region, N1 is the refractive index of this particular region. So if you have some thin film sample where the thickness of your sample is of the order of wavelength of the light, visible light, then you can basically use that particular analysis. I know that all of you have basically studied the interference in thin films. So you can use that particular to estimate the value of refractive index of your material, which is basically the semiconductor material. But for this purpose, your sample must be optically transparent. Okay, means for example, if you are working with titanium oxide, zinc oxide, something like that, thin films on some type of substrate, then you can basically estimate the values of optical constant, which is the refractive index and attenuation coefficient, using the transmission measurement. Okay, and you can basically you know that the refractive index is not really constant; it's a function of energy or wavelength. So you can basically estimate what is the value of means how this particular refractive index varies as a function of energy of the light. Okay, so conclusion so far, you can basically use optical absorption spectroscopy not only to probe the band gap, but also to find out the electronic disorder near the band edges, which is called Arbeck energy. It can be used to find out the what kind of defects present in the circuit, and obviously for the optical constant. Okay, so now let us see what else you can do using optical absorption spectroscopy. Okay, so this is the one of the example which I am basically quoting here. Barium titanate is one of the ferroelectric material which is known from decades or from really a century now. Uh, uh, and this particular sample is known to show various structural phase transition. Means at higher temperature beyond 120 degrees Celsius, it's a cubic. Then near room temperature, it's tetragonal. If you further lower the temperature, means just below 0 degrees Celsius, it's orthorhombic. And if you further decrease the temperature, then it shows the rhomboidal phase. So this is something which is well known to the material scientists from decades. Okay. So now what we have done is that we have basically modified our optical absorption setup, and we have basically this is the in-house development what we have done. We have basically put some heater. We have basically designed a heater, and on this particular top of the heater, you can basically keep your sample, where you can now change the temperature of the sample, and now you can basically perform the optical reflectivity as a function of temperature. The details of this particular setup is given here. So what happens that, as I said, that you can basically perform the optical spectroscopy as a function of temperature. And now the thing is that all of us are aware of something which is called chronic Pinay model. Okay, what chronic Pinay model says that whenever there is a change in the lattice parameter, the value of band gap or the periodic condition, there will be modification in the value of band gap. Okay, so at the structural phase transition temperature, you know that there is a change in the symmetry, which will basically modify the expected to modify the band gap. Okay. So now we have performed the reflectivity experiment as a function of temperature. From the reflectivity data, we have find out the band gap. And now what we have done is that we have basically plotted the band gap as a function of temperature. And you can see that we have basically performed the high temperature measurements from room temperature up to close to 500 K. So you can see that the temperature at which the sample goes from tetragonal to the cubic phase, at the same point there is a significant jump into the value of band gap, or there is an anomaly. And this particular anomaly is essentially due to change in the symmetry of barium titanate sample. Okay, so if you look into the other studies on barium titanate, where the scientists have measured the lattice parameter as a function of temperature or dielectric constant as a function of temperature, what they could see that there was some hysteresis at the phase transition, because it's a first order phase transition. And we thought that we will also perform similar studies. So we have basically measured the band gap as a function of heating and the cooling cycle, and but the value of hysteresis was not really promising. It was within the error bar, so we can say that there was no hysteresis. But what we have done is that we have performed, when we performed this particular experiment to estimate the value of band gap, we have also measured the Arbeck set, the value of Arbeck set. So in heating and cooling cycle both. So when we have done when we have basically plotted the value of Arbeck states in a heating and cooling cycle, we could see that there is a significant hysteresis here. Okay, so what does it mean? It means that in a case of optical measurement, The airbag, the measurement of airbag tail shape in a heating and cooling cycle will provide the better information as far as the region of hysteresis is concerned in a case of barium carbonate. So that was something which is, and if you perform some additional physics analysis, means if you basically want to plot the stress exponent coefficient to find out what is the relaxation time, or whether that there is a metastable state present into the means basically whether it's a first order or second order phase transition, then you can basically perform this particular experiment as a function of time, and you can see that what kind of dynamics that particular first phase transition is basically following. So this is something, the additional information which you can basically get if you basically add some temperature dependent attachment to your system, and this is the paper on that particular area. So so the conclusion of this part is, you can say that, as I said, the electronic disorder of the orbital is a accurate parameter, order parameter to examine the phase transition. Okay, so the overall conclusion, what you can basically say is that you can basically use optical absorption spectroscopy not only to find out the band gap, but you can also find out the electronic disorder. You can also probe. The defect, position of the defect level, whether it's due to oxygen type of defect or due to some other type of defect. And you can also use this particular spectroscopy to find out the phase transition. So with this, I would like to stop here, and I would like to welcome the questions from the audience, if any.
Thank you, Sandeep sir. Now the session is open for discussion. Anyone having any query or question? Again.
Respected sir, very
Yes.
effective presentation.
Thank you,
I
sir.
know for barium titanate,
Mhm.
when we are changing the band gap,
Mhm.
then there is change in refractive index of barium titanate.
Yes, yes, yes. That's
Is
happens. Yeah.
some mathematical relation with temperature variation and band gap variation for refractive index of barium titanate is available in literature?
Yes, sir. I think, means, for example, as far as this band gap is concerned, you know that the actually refractive index and dielectric constant are related, and dielectric constant and band gap is related due to something which is called Mohs formula. So I think there must be some literature available. In fact, as far as temperature dependent of band gap is concerned, there is something which is called Varsney's relation and Einstein single oscillator and double oscillator model, which are basically used to model the temperature dependent of band gap. And I know that there must be some additional models of available to basically model the refractive index as a function of temperature.
Okay, thank you, sir.
Yes, any other question from here? Audience, please. Any question from this side?
Actually, not really clearly audible. Maybe other can mute their mics.
Ma'am, can you repeat the question? Question was not properly audible. Can you repeat the question, please? Okay, I think connectivity issues there. So we can proceed for next question. If there any question.
Or otherwise, I will request to type that particular question in the chat box.
Yeah, that is better.
Yes. Yes. You can type the question. If connectivity issues there, you can type the question.
Chat box on.
So they are able to hear your voice.
नहीं वहां से वो माइक ऊपर है तो आपका साउंड जा रहा है
Okay, so as far we have no question now, so I think we should stop this session. I'd like to thank Dr. Sandeep sir for his time and valuable talk. We are really mobilized and it was really nice to listen you here. Thank you so much, sir.
Thank you, madam. Thank you very much.
One question. So, this question is related with the advancement in the semiconductor field in India. As our government has promised India to be the root of the world, in particular in the area. Your lab is working in the semiconductors. Could you brief that how we can contribute and how much we can fulfill the dream of our Prime Minister?
Yeah, that's a really very good question. Actually, you know that there is not really a very simple answer to this particular question. But what I personally feel is that means wherever we are, we must be very much honest with our job or with our role. Means if I am a father, then I must be very much means I must basically very much responsibly take that particular role as a father. If I'm a teacher, I must be responsible as a teacher, okay, and I must be honest with my job. Actually, what I personally feel is that means as a country we have huge population and huge means I will say excellent brain. You know that in our region, especially the Vidarbha region, you know that Professor Mande, he was the Director General of CSIR. His father, Chintamani Mande, he was one of the expert in the X-ray scattering. So we had lots of stalwarts present in our own region. But I think that if we basically work like these people very honestly with our full honesty, and obviously I think that we will be able to purify the raw material. Means, for example, the silicon is really present in our India like anything. And I think to the best of my knowledge, we have silicon in our mines, which is as good as 99% pure, but we cannot make it 99.999% pure. So that is our problem. So if we really want to really fulfill the dream of our Prime Minister to make this particular country a semiconductor hub, we must produce purest form of semiconductor. So since we have 99% pure silicon, but we are unable to produce single crystal silicon wafers in India. So that's a practical reality. So if we really aim to do that, we will be successful. But what happens now? We are only money minded. So our industries are consumer oriented industries, not research oriented industries. So we must produce the industry which are research oriented industries, and where we will be able to really make these pure semiconductor. And once you have pure semiconductor, then obviously you will able to produce diode, transistors, and ICs, means very highly complicated, I will say chips, for example, Intel, Pentium, and all those chips we will be able to make here in India. The only thing is that means the physicist and the chemist, they must work coherently to make to first to really produce a very purest form of semiconductor. So that's what my personal opinion is.
Thank you so much, sir, for fulfilling the dream of this conference. Material should be applicable for the society and best wishes for new years, for your launch and obviously semiconductor. Thank you so much for your enlightenment and everything.
Thank you, madam. Thank you very much. And it's really my pleasure to give this talk here in this particular hall, where I could see the photo of means it's something like a Pandharpur for us. Means Anandvan is like a Pandharpur for us. So thank you very much for the invitation.
Thank you, sir. Thank you for your time. Thank you so much. With your kind permission, I am ending this session here. Thank you. Thank you, sir. We are honored to have session chair 7, Dr. Shubhi Pandey and Dr. Kavita Gaur, who ensure us with their expertise and experience to facilitate the session and who ensure us a smooth and engaging discussion. So we are very privileged to be the honors of the session chair. And I request Sir Bansur to kindly do the honor of Dr. Kavita Gaur.
इथे करायचं ऑफलाईन इथे करायचं
ऑफलाईन झालं सर
पार्टिसिपेंट म्हणजे
काहीच नाही फक्त फक्त ऑनलाईन ऑनलाईन वाटली
एक ऑनलाइन बंद सुरू ना ठीक है अभी इसको
आपण सारखं सुरू कर दिया
एक सेशन आहे
हाँ सेशन
नागपुर के बंद से कौन से
अमित बंसू
नागपुर पे
अमित बंसू
हाँ वो सेशन चाहिए
निजामुद्दीन सर है एक बंसू
वो चालू करना है
सर है आशीष चालू कर रहे हैं तो बता वो शुरू हो गया था आशीष चालू कर
तो अभी क्या करेंगे
चल रहा है
अभी यहाँ
यहाँ सर बोला तो यहाँ शुरू करेंगे लेकिन यहाँ लेट हो जाता है यहाँ कुछ ठीक है
तो एक काम करते हैं वो जो चालू है
क्लिप दिखा दीजिए डॉक्यूमेंट्री वाली डॉक्यूमेंट्री की क्लिप दिखा दीजिए
हाँ वो दिखा दो वो अनाउंसमेंट कर दो आप अनाउंसमेंट की क्लिप है आपका सर्टिफिकेट सब लेकर रखा है
हाँ
मेरे पास रखता हूँ
किशोरी का लेकिन
किशोरी का मेरे को वो भी रखता है उसको वर्कशॉप भी बना दो
किसका
किशोरी का
किशोरी का
वर्कशॉप के लिए
हाँ बना देना
बना देता हूँ दोनों हो जाए
Sure. Ladies and gentlemen, it was a very short and documentary clip of Anand Gavardhan. So we will definitely enjoy the short documentary film.
हाँ तो ऐसे बोल सकते
The leprosy patient who then works on Tamil is a person who is being left out by his family. His family does not want to do the thing because he is somebody who has a disease which has no solution to. A lot of you believe that leprosy is eradicated from India. But the World Health Organization, which published its reports in 2012, even today says that India, Texas, India, Brazil, Indonesia are the top 3 countries with leprosy endemic. More than 2 lakh cases are found every year. Quoting the bar, which says every 4th minute there is a leprosy patient who is detected. Are you even aware? I wasn't. I wasn't aware that leprosy is such a great issue. I wasn't aware that leprosy patients' rehabilitation is a challenge. I wasn't aware that the leprosy person who wants his cure can do so many things in life.
सपनों के बाद इंसर्ट में वो एडिट हो गया और ये 14 में रिएक्शन आया तो 16 ये 35 साल मेरे नाम है क्या क्या हमारा कानून बुद्धि का दरदुरा यार सभी कहते हैं तो में लड़के जन्म लड़ने और Teman-teman, dan juga mesti menyediakan pekerjaan dunia setelah semua ini jadi menjadi sama desa masuk tadi orang memang suatu yang terkait ini.
Yes, sir. Yes, sir. Is it audible? Yes, sir. Yes.
Sir, I have.
Yes, sir. Even today, every day on average, one legacy afflicted person walks up and on ground. The age group is from
You
20
unmuted.
until citizenship. When he walks in here, stamina is descended.
Uh,
The first thing that we do is we have
yes, sir. Can I
because mental counseling
audible?
is that because of the social stigma that it works with after mental counseling, treatment, the physical rehabilitation impacts getting him back to the mainstream. This person is witnessing impressive. He does not understand what needs to be done. As the leprosy grows up, his sight reduces, he develops anesthesia, there is claw and fingers, which you see with a lot of leprosy affected people. This rehabilitation calls for giving up leprosy these medicines, but at the same time, the care diseases which says we have to also feed that. With all of this, once he's basically make him stand on his own feet, that is we tell him what we can do. We give him livelihood opportunity where he can be engaged in, and thereafter he starts working. Today, where do we have a Canada? We have education, healthcare, livelihood, agriculture, and a beautiful model of rural development. And if we put all of this together, it calls for a smart innovation.
Sir, Dr. Vaishnav.
माझं कसं आहे काय माझा जन्म हा अडकवाड्यातच झालेला आहे माझे पप्पा आणि माझे दोघंही इथंच काम करतात मी पण 11वी कॉमर्सला एएनसी कॉलेजमध्येच आहे आनंदमध्ये मला खूप छान वाटलं कारण इथे एका फॅमिली सारखं वाटतं सर्वजण मिळून राहतात कोणत्याही गोष्टीची गरज असल्यास जे आपले शेजारी वगैरे आहे ते पण खूप सपोर्ट करतात शिक्षणाबद्दल पण खूप छान आहे आणि इथे सर्व ग्रुप मिळून जे टीम वर्क करतात तसं पण आहे इथून काम करायला पण आम्हाला आवडेल कारण आम्ही जसं बाहेर जाऊन काम करतो त्याच्यापेक्षा इथे काम केलेलं आम्हाला जास्त छान वाटतं आम्ही त्या ठिकाणी श्रमदान करतो त्या श्रमदानामध्ये आम्हाला फ्रेंड्स मिळून कॉलेज वगैरे पूर्ण कॉलेज पासून सुट्टी मिळालेली असते आणि श्रमदानामध्ये जाऊन खूप मित्र मैत्रिणी सतत वर्क केलेलं आम्हाला खूप छान वाटतं
Good afternoon. Sir, welcome Sankar sir to this March 2024.
Am I audible?
Am I audible, sir? Hello.
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 Hello. Am I audible?
Yes, sir. Yes, you are audible. We'll begin session soon, sir.
Yeah. Thank you.
Yeah, I request Dr.
Good
Stuti
afternoon.
to
Good
session, sir.
afternoon, all of you. And we will be starting our for this, and we'd like to welcome Sir, and my to introduction here. So, with permission, I'd like to read introduction here. So, is a professor at NIT, Nagpur. Sir is listed in world's top 2% scientists for executive year 2020 as per the University has ranked less than 500 as per the scientific index data. As material science scientist India as per the .com, 134 India 2024 as second term Dr. Sangpal serving as head Department of Physics and Chairman Board of Studies Physics and served as Associate Dean exam half for VNIT and working member of Senate VNIT. As HOD Physics VNIT successfully received DST FIST grant 219 lakhs after obtaining PhD from Shivaji University in 2000. He worked abroad for more this GSPS doctorate fellow associate. Dr. has 20 years of teaching and 7 years of research experience. Worked as assistant professor or 4.0 in 2000 as a associate professor. One is Young Scientist Outstanding Work Presentation Award by Material Research Society Japan in 2005. Department of Science and Technology DST, Government of India to participate in the meeting of Nobel laureate in Landau, Germany, 2001. Dr. Sangpal guided 17 PhD students. Among six got opportunity to work abroad in Germany, Spain, Israel, Denmark, Japan, and South Korea. He has edited one book entitled Simple Chemical Methods for the Thin Film Deposition, Synthesis and Application, published by Springer, and he has contributed three book chapters, two in Springer and one is in elsewhere. On his two Indian patent, 190 publications with average impact factor above 5, with Google Scholar H index of 2, having citation above 8,400 with average citations 40. He has 10 major research projects on his credit, worth rupees 2.82 crore from DST, SERB, DAE, BRNS, UGC, and UGC DAE funding agencies. He has arranged two short-term training programs and one national conference. He is fellow of Maharashtra Academy of Science and member of Institute of Physics, IOP UK, Indian Association of Physics Teacher, Indian Science Congress Association, Material Research Society of India, visited Sweden, France, Switzerland, Holland, Belgium, USA, Germany, and Japan for delivering invited talks and attending meetings. In 2018, he was nominated for Shanti Swarup Bhatnagar Award by Director VNIT. He is serving as an expert committee member, AICT, expert panel member for DST projects and expert reviewer for the SERB and DAE BRNS project evaluation. Research expertise include device gadgets, superconductor, solar cell, gas sensor based on nanomaterials, thin films, and many more. So, with this brief introduction, I'd like to invite Dr. Sangpal sir for his valuable talk. Please, sir. I invite Sangpal sir to proceed with his talk. Yes, sir, you are audible. I think there is some connectivity issue. We are shortly starting his talk.
Full screen is visible.
Yes. Yes, visible.
Hello.
Visible.
Am I audible?
Yeah.
Yes, sir.
Okay. Uh, and screen is full screen is visible.
Yes, sir. Yes, sir. It is full screen is visible, but it is not on presentation mode yet.
I
But the
think there is
screen is
some issue.
visible.
One moment. Let me
Yes, sir.
stop again.
We can see the PPT, sir. First slide is
No,
visible.
but that should be full screen because some animation is there.
Okay. Okay. Yes, sir. Request participants to please keep your mics on off mode.
And now,
Yeah, it's coming. Yes, sir. It is now visible.
okay. So thank you very much for the nice introduction. So I'm giving here with a talk entitled energy conversion and storage. That is the state of art from synthesis to device grade development. As this conference, it is of the grand success as it is an international conference, and the idea behind this conference it is material synthesis and applied science which can be applicable for the society. So here I made the title which is applicable for the society through energy conversion and storage by means of solar cell and storage by means of supercapacitor, and how we have developed this at the device grade development, so that you can see the developed device in the laboratory inside this one. So basically, whenever we are thinking for the energy, there are two things which are important. One is the energy conversion, and second one is the energy storage. So basically, if you are thinking about the energy conversion, we can utilize the free sunlight which is available, so that we can use the concept called the photovoltaics to convert light into the electricity, and whatever electricity it is generated it can be stored by means of the device called storage device. That can be capacitor, that can be batteries, that can be supercapacitors, so that we can utilize this converted energy, we can store that one, and then we can utilize for the household application. So basically, I am going with this talk into the two parts. One is the energy conversion by means of solar cell and energy storage by means of supercapacitor. So whenever we are thinking about the energy conversion, that is the solar cell, we can think about simple PN junction type of the solar cell. But here I am giving little bit different idea called as a colorful solar cell. So colorful solar cell, it is based on the concept called as a dye-sensitized solar cell, which can be low cost and low temperature processed solar cell, so that we can use the simple chemical method to develop this solar cell. And the chemical method can be utilized to deposit different materials that can be in the thin film form. Like here, I wish to demonstrate about the zinc oxide, so which can have an attractive application along with sharp cut in production cost. So whatever the process it is there, that should be environmentally benign. So also we can think about the different approaches are coming up, so that your solar cell can be colorful. See-through means it can be transparent or translucent, we can say. And if it is flexible, then it is possible to bend your solar cell. And if it is lightweight, so that you can hang up this solar cell. And if it is cheaper, so it can be having great applicability for the society. So basically, we can think about how this dye-sensitized solar cell works, because for many of you may not know about the dye-sensitized solar cell concept. So we can go through this one, and those who are beginners, it can be very helpful, this concept called as a dye-sensitized solar cell. So I have placed this one into two parts. One, understanding on this one through the schematic called as a cross-sectional view, and second one on the basis of the energy band diagram. So as a scientists, we can understand in the both the way on the basis of energy band diagram as well. So here you can utilize the wide band gap semiconducting material as a TiO2 you can use. Wide band gap means what? Having the energy band gap greater than 3 electron volt. So you can quote on this one on the TCO layer. So TCO, that is called as the transparent conducting oxide, you can utilize as a fluorine doped oxide or maybe indium doped oxide, which can be coated on the glass as a substrate, and where you can coat wide bandgap semiconductor like TiO2, on which you can coat one monolayer of the dye. So band gap of the wide materials, it is greater than 3 electron volt, so that whatever visible part it is there, it can pass through this wide band gap and light can fall on the one monomer of the dye. The basic requirement of this one, as material should be wide band gap, it should have high surface area, it should have interconnection of the nanoparticle on which you can coat one monomer of the dye, so that you can get better absorption for the visible part of the solar spectrum. And then you can place the liquid electrolyte and cathode, that is platinum coated as a active layer as a back contact. So when you can illuminate the light, that is the visible light, on this type of the solar cell, light can pass through this wide band gap material, which can fall on this dye molecule, so that electron can excite within this dye, so that this excited electron can transfer to the conduction band of this TiO2, and this electron transferred through the external circuit that is called as a load towards the electrolyte, and this cycle it is completed and electricity it can be generated. So this is a simple way how we can understand this type of the solar cell. So now you can see through this schematic how it is working. So you can illuminate this one with this sunlight, that is the solar cell. And here blue color, you can see that this generated electron within this dye, it can transfer through the wide band gap semiconductor to the TCO through the load towards the electrolyte. And this cycle it is completed and electricity it is generated. So this animation is visible clearly. Yes.
Yes, sir.
Okay. Yeah. Thank you. So this generated electron can pass through this load towards the electrolyte, and this cycle it is completed and electricity it is generated. So world record efficiency it was achieved, that is more than 11%, and now it is 12, 14 to 15% it is there. So we thought to use the zinc oxide by using chemical method. Mostly for this dye-sensitized solar cell, titanium dioxide it is used for this one, but we thought to use zinc oxide because zinc oxide it is possible to deposit by using chemical method, and whatever the processing temperature for TiO2 it is mostly 450 degrees Celsius, but we thought to use zinc oxide so that we can deposit this zinc oxide at lower temperature as compared to the temperature which is used for TiO2. So what we are using simple chemical method where we can use simple beaker system. So this is process we can say it is a low cost, where we have used FTO coated glass substrate and we are dipped inside the zinc precursor. So precursor what we have used is simply zinc acetate and hexamethyl tetraamine, and deposition temperature just room temperature. So we have varied this deposition time from 20 to 40 hours to optimize that one, and we have heated that one. That is the annealing temperature. We dropped down to 200 degrees Celsius to convert zinc hydroxide to pure zinc oxide. And this is the photo image of the pure zinc oxide. But our target it was to make this zinc oxide at temperature lesser than 100 degrees Celsius, so that you can use flexible, that is PET ITO, so that you can bend this type of the solar cell, but we have not succeeded. We have succeeded up to 200 degrees Celsius to completely convert hydroxide part to pure zinc oxide, which is the requirement in the dye-sensitized solar cell application. So we have use the characterization technique like X-ray diffractiometer to analyze whether deposited material it is zinc oxide or not. And after annealing, we find out that deposited zinc oxide it is having hexagonal structure. But the basic requirement for the dye-sensitized solar cell is that your material should be having wide band gap. So we have obtained this one as the material band gap estimation, as it is greater than 3 electron volt. So it is about 3.27 electron volt for this zinc oxide. So, but next requirement it is there, it should have the high surface area. In order to get the idea about high surface area, we have taken a SEM image for the zinc oxide where you can see the petal-like morphology. But another requirement it is that it should have high surface area with interconnection of the nanoparticles. In order to get this insight for this one, we have zoomed this one image at 100 nanometer scale bar, where you can see that morphology is like cactus-like morphology, where interconnection of the nanoparticle can be clearly visualized. And this zinc oxide with characteristic morphology gives very high surface area on which you can coat one monomer of the dye molecule. And this result it was published inside the Jalcom journal. So how we adsorb these dye molecules on the zinc oxide just by dipping this zinc oxide coated FTO, dipping inside the ethanolic solution of the dye. So where one monomer of the dye it was coated, then we have placed platinum as a back contact, and liquid electrolyte, that is polyiodide, we have used as a liquid electrolyte, and we have completed this device where zinc oxide coated with the dye serve as anode and platinum as a cathode material in between electrolyte we have introduced by using capillary action. And this is the schematic of the dye-sensitized solar cell. So basically, if you are using TiO2, you require the dye with NCS glue so that it can attach very well, chemical attach very well with the titanium dioxide nanoparticle. But whenever you are working on zinc oxide, you require the dye with the carboxyl group. So we have chosen the dye which is eosin Y from the xanthanum series, which having carboxyl group which can attach very well on the zinc oxide. And here this eosin Y, it is red in color. So this is the absorption spectra for this dye which is red in color, and its beauty is that it's red in color, but drawback is that it is having narrow absorption from 500 to 550 nanometer. But still, we have adsorbed on the zinc oxide, and we have optimized this one for 1 by 1 centimeter square. And what we observed is that it shows the efficiency greater than 2%. So this is by using simple chemical method deposited zinc oxide, which is at the lower cost and area, it was 1 by 1 centimeter square. It gives efficiency of about 2%. But beauty is that it is red in color. And here you can see that we have just used crocodile pin to assemble this device, and we have tested almost for 3 months. Just we have introduced the liquid electrolyte because there is no perfect sealing. Still, this works very well under the light intensity, 100 milliwatt per centimeter square with AM 1.5G. Again, this result, it was published inside the Solar Energy Journal. You can go through this one, different parameter we have listed. In order to get better absorption, we have used another dye, which is having also carboxylic group, that is called as the D149 dye. But this absorption, it is better than the eosin Y. That's why it gives the efficiency about 3.5% for D149, which is adsorbed on the zinc oxide. This result also published inside the material letters. Also, we have tried with another dye called N7919. It gives the efficiency about 3%. So what the colorful approach that we did, whatever the solar cell that you can see at present may be that black in color or blue in color, but we made little bit different approach as a colorful approach. As you can see that this is a spectrum which contains blue color, yellow color, as well as the red color. The reason why that we have used for the red color. Then another dye that is called as the Coumarin 343, which is also having the carboxyl group we have used for yellow color, and methylene blue with blue color, but this is not having carboxyl group, but rather it is having chromium group. And this is the absorption spectra for individual dye, that is yellow color, red color, and blue color. Blue color gives very good absorption, but it is not having carboxyl group, but it is having chromium group, and we are adsorbed on this zinc oxide. And here you can see at the bottom, red color, yellow color, and blue color, which is adsorbed on the zinc oxide. And each dye gives its own efficiency about 2% for eosin Y, about 1% for Coumarin 343. But methylene blue dye, it gives very low efficiency as it is not having carboxylic group, although it is having very high absorption in the visible part, but it is having rather chromium group. Now, what we did as an advanced colorful approach, as you can have three color in your hand, that is red and blue and yellow. So why not to mix two color to get third color? So we have tried this one by mixing red color with yellow color to get orange color. If you are mixing yellow color with blue color, you can get green color. If you are mixing red color with blue color, you can get violet color. So we have tried with only with orange color to make the cocktail dye, or you can say it can be blended dye, just by mixing red color with orange, yellow color to get orange color. And this is the orange color dye that we absorb on the zinc oxide. And here you can see this is absorption against the wavelength for the mixed dye. And this blended dye, it can use the coverage in the both the part yellow as well as the red color, so that this orange color it absorption used in the yellow as well as the red color, and also for this quantum efficiency against the wavelength. And this is for completed device that is called as a incident photon current conversion efficiency, called as a IPCE against wavelength. And for this completed device as well, it gives both the coverage from yellow part as well as the red part. And beauty is that this orange color dye gives better efficiency as it covers both the part of the yellow as well as the red part. So it gives the efficiency about 2.25% for the blended dye. Not only this one, we have tried different dyes like rhodamine B, rose Bengal that is for pink color, brown color D149 dye, red color that is for eosin Y. So here you can see that each dye is having its own absorption, that is the intrinsic property. It gives different efficiency depending upon its absorption. We have tried from 0.02% to about almost 3.5% efficiency for the different dyes. But beauty is that you can have different color in your hand, and also orange color you can use about 2.25% efficiency. What is the use of this one as the colorful dye? For example, this was published inside the Journal of Photochemistry and Photobiology. Here, example is that whatever color is there, if, if you want to replace with this type of the solar cell, so you can replace, for example, if your roof tile which is red color, you can replace with erosion by diadsorb zinc oxide as a solar cell, so that you can use for the attractive application. Also, you can use for light to electricity conversion. And this we have tested for the completed device in the laboratory. As here you can see that this is a digital watch as well as calculator. For this one, what we required 1.5 volt battery cell, and that we have removed and we have connected this one by three solar cell in series. Each solar cell gives zero point 0.5 volt. This is for eosin wire we have tested, which can use about 1.5 volt. And here you can see the photo image of this solar cell to run up this digital watch as well as the calculator. So here you can see this is the actual video of this one. Can you see this one? Video is visible?
Yes, sir.
Yes, sir.
So here this is in the dark and this is the light. So whatever this zinc oxide, again, once again, I can repeat this one. So this is just the zinc oxide where we absorb eosin Y as a dye. And this you can get the actual satisfaction that your device it is working well. Publication it is one factor, but another satisfaction of your working device to give the demonstration is another. So this is for light to electricity conversion. So what is the advantage is that, for example, just I mentioned roof tile, for example, D149 dye or eosin white dye, you can use for the attractive application as well as for light to electricity conversion. So, for example, if your stop signal or maybe no parking signal, which is in the sunlight, but it is red in color or maybe blue in color or maybe yellow in color, you can replace with this type of the solar cell. So, attractiveness is the one concern, and second one, light to electricity, it is the another concern that wish to highlight inside this one. Now, whatever the solar cell it is there, these are the low cost solar cells, because whatever dye that we are going to utilize, it is very low quantity, that is in the micromolar, and dyes cost it is also lower. And whatever method that we have adopted, these are at the lower cost, because we are using only simple beaker system and the substrate to deposit the zinc oxide. And whatever the process it is there, it is environmentally friendly without any clean room environment. So next approach it is there, whatever the electricity is conversion, it is there, how we can store that one. We can store that one by means of maybe capacitor, we can store that one in terms of the battery. And third one, it is called as a supercapacitor. This is the new concept which is emerging out for the energy storage devices. So supercapacitor means what? It is the electrochemical energy storage which is having high energy density than the ordinary capacitor and high power density than the batteries. So what is the energy? Energy means capacity to do the work, and power means what? How fast energy can be delivered. But the supercapacitor, it bridges the gap between the batteries and conventional capacitors. But present scenario, it is going on to focus to have improvement in the energy density so that you can replace this type of the energy storage device by supercapacitor by batteries so that it can have added advantage is the higher life cycle. So what are the parameters it is there which can distinguish supercapacitor with respect to other energy storage device? And here you can see that this is the Raygon plot which can clearly distinguish between the capacitor and the battery so that you can think about the supercapacitor, whatever parameters are there which which are in between of the capacitor and the batteries. So capacitor it is having higher specific power, batteries it is having higher specific energy, supercapacitor it is intermediate of this one. So batteries can have higher energy density and capacitor it is having higher power density. In order to differentiate this one in terms of the parameter, capacitor requires very less charging time as well as it gives very less discharging time. So it is in microsecond to millisecond. And battery requires certain minutes to certain hours to charge. But supercapacitor can charge within minute and discharging time it is in between the capacitor as well as the battery. But here you can think about the battery because battery presently e-vehicles are coming. It's a very hot scenario so that batteries are going to utilize they are using this one inside the vehicles, but battery is having higher energy density than the supercapacitor. Suppose if you are making the supercapacitor comparable to that of the battery having the energy density, then it is possible to replace this battery with the type of the supercapacitor. But added advantage of the supercapacitor is that if you're using the battery, you can use, for example, 3 years or 4 years because its cycle life is lesser. It may be 2000 or it can be maximum 3000. It is there so that you have to throw that battery. And if you're comparing the, for example, moped for the battery cost, it is there. It is one third of that moped. So again, you have to utilize that cost. You have to pay that cost after 3 years or 4 years to purchase that battery. So if you are replacing with this type of the super capacitor, if it is having high cycle life, for example, 5,000 to 10,000 or maybe 50,000 cycle life it is there. So then it can run up to 10 years or maybe 15 years so that you can replace this super capacitor if it is comparable energy density as that of the battery. So we thought to work on this supercapacitor to replace this battery so that battery can be possible to replace in terms of the e-vehicles are concerned for the future technology. Another disadvantage of the battery is that most of the batteries are using liquid. So we thought to use liquid-free supercapacitor. We are calling as a completely solid-state supercapacitor. Added advantage is that it can be made flexible so that you can bend this type of the supercapacitor so that it can have added advantage for future electronics. So supercapacitor, as one example, in Shanghai, one bus it is running when people are riding inside the bus, this supercapacitor gauge charge, and then it can run up to 5 to 10 kilometers. And during that one, it can discharge that one. And again, in the next ride, when people are going inside, the supercapacitor can charge. But whatever the supercapacitor they have used, it is liquid based and it is having lesser energy density. If it is possible to have supercapacitor, it is liquid free, having high energy density comparable to the battery so that it can run up to 50 to 100 kilometers. It is possible that can be the future trend. And here you can think about the supercapacitor which are alternative to the batteries. Not only this one, if you are making the supercapacitor flexible, it can be variable too so that you can have advanced application like wearable electronic devices. Now you can see that some smartwatch may be there which can be flexible. Now you are thinking previously whatever TV it was very big in size, now it is flat. Maybe in the future you can have the TV which can be flexible so that for this type of the electronics we require the flexible or bendable type of the energy storage device. So we thought to use the concept called as a flexible solid state supercapacitor. I wish to demonstrate here. So as a new concept, as a supercapacitor, we can understand that one. How much time it is the sir?
So you can proceed. I mean, you can take as much of time you need for.
Okay, just 10 minutes we required. So
Yes, sir. Yes, sir. Sure.
supercapacitor we
Please.
can distinguish. Supercapacitor we can distinguish into the two types. One it is called as a EDLC, called as a electrochemical double layer capacitor, and second one it is called as a pseudo capacitor. So whatever storage mechanism it is involves inside the EDLC is the charge separation at the electrode and electrolyte interface. And mostly carbon-based materials, these are used inside this type of the EDLC type of the supercapacitor. But here, whatever the capacitance, it is the low capacitance because it is just surface area reaction, it is there. But added advantage is that it is having very high stability. But in case of the pseudo capacitor, Faradic reaction it is there, where oxidation and reduction process it is there. Metal oxides, metal chalcogenides, polymers are used inside the pseudo capacitor. But added advantage of this one is that it is having high capacitance, but the disadvantage is that it is having low stability. So each type of the supercapacitor is having its own advantage as well as own disadvantage. ADLC, it is like a simple capacitor. Pseudo, it is simple like a battery. So what we thought to have the hybrid capacitor, which is the combination of the EDLC as well as the pseudo. So for this EDLC, carbon nanotubes, graphenes, carbon aerogel, activated carbon can be used for the EDLC materials. And from this one, we have picked up the carbon nanotube, which are commercially available because it is having one directed conducting path with very high surface area. And from the pseudo, we can use polymer, metal chalcogenide, metal oxides we can use from this one. So if you're using composite or you can say hybrid type of the supercapacitor with the combination of the carbon nanotube, which is having high stability as well as high conductivity, with metal oxides, with metal metal oxide, metal chalcogenide, or polymers, which is having high capacitors, it can have improved electronic conductivity with well-directed conducting paths so that it can have dual charge mechanism. So what are the material requirements for the supercapacitor? Are high conductivity, large surface area, good chemical stability, and good reversibility. So it has to satisfy inside this hybrid type of the material. So what the material we have focused to the surface architecture. We have used simple stainless steel substrate which is available in the market, which can be very thin so that you can bend this type of the substrate on which you can coat different type of the surface morphology that can be nanoflex, that can be nanoparticle, that can be nanowire, that can be core shell type of the morphology. We have tried also carbon nanotube which is commercially available. Then we thought to use carbon nanotube as the ADLC type of the material on which you can coat the nanoflex, you can coat the nanoparticle, you can coat the quantum dot, you can coat the polymer, which shows the pseudo type of the behavior. Because carbon nanotube, it is EDLC type of the behavior on which you can coat the nanoflex, nanoparticle, quantum dot, polymer with the pseudo type of the material so that you can make the hybrid type of the supercapacitive electrode. So just as the one concept I can explain you as the vanadium oxide, which is the pseudo type of the material we have coated on the carbon nanotube by using simple chemical method to form the symmetric type of the supercapacitor. So how we have coated this carbon nanotube? Just we have used yes, just we have used a deep and dry coating technique. So we have made the gel, which is a mixture containing solvent and solute. Here, solute it is carbon nanotube. Then we have just dipped the stainless steel substrate inside this one, and then we have dried under the IR lamp so that carbon nanotube coated on the stainless steel substrate. So this is simply deep and dry coating technique. It is there. This is stainless steel which is coated on this, and then we have used IR lamp to dry that one. Number of cycle can give your preferred thickness, how much thickness you want that one. You can coat that one for the number of times so that it can be coated. But you should remember about the substrate surface properties, whether it is hydrophilic or hydrophobic it is there, and linker between the substrate and material to be deposited. So sometimes you require the surface activation to adsorb carbon nanotube. It can be electrochemical activation, sometimes surface passivation or nucleation center formation it is there whenever you are using deep and dry coating technique. And this is the carbon nanotube that we have coated on the stainless steel substrate. This is it shows the EDLC type of the behavior on which we have coated vanadium oxide just by using chemical path deposition. So chemical path deposition involves the cation and anion together, and we have used vanadium sulfide with NaOH solution and just deposition temperature just 60 degrees Celsius. And we have used X-ray diffraction pattern to identify this carbon nanotube on which vanadium oxide it is there or not. So this is surface morphology. First image, it is just SEM image for this carbon nanotube. Second image, this is vanadium oxide when we have coated just on stainless steel without any carbon nanotube. It gives flex-like morphology. And then when we have coated this vanadium oxide on the carbon nanotube, this flex coated on the outer surface area of this carbon nanotube, which gives very high surface area. And in between, you can see there is an empty space. This empty space can be utilized to penetrate this electrolyte, or if you are forming the solid state, you can form the gel which can be penetrate inside the porous area, so that very high surface area electrode can be utilized so that your specific capacitance can enhance. And this is a TM image where you can see that flex can be coated on the carbon nanotube. So small flex you can see on the carbon nanotube which is coated, and we have done PDX mapping as well. So in order to optimize that one, initially we have optimized with the electrode which is coated on the stainless steel, that is vanadium oxide on the carbon nanotube. And for this one, we have used 3 electrode system: reference electrode as AgCl, counter electrode as platinum wire, and carbon nanotube which is anchored with vanadium oxide as a working electrode. So here you can see that specific current versus potential with reference to AgCl gives the area under the curve. You can see hysteresis type of the curve. You can see here area under the curve gives the amount of charge it is stored. This black curve it is for carbon nanotube. Then the red curve it is vanadium oxide, and blue color it is for vanadium oxide coated on the carbon nanotube. And here 0 to 1 volt, it is the potential window for the carbon nanotube we observed. And whenever we are putting on this vanadium oxide on carbon nanotube, area under the curve, it enhances drastically. And this is the formula that we have used to calculate the specific capacitance. And we observed about 1238 Faraday per gram of the specific capacitance at 2 millivolt per second. Not only this one, we have tested this one for almost 4,000 cycle. And so we have done GCD studies. Because of the lack of time, I am now showing here. And this is for 4,000 cycle, which is almost 93% stability it is there for this electrode. And this electrode gives the potential window that is 1 volt. So whenever you are making the device with the liquid, there is certain problem called liquid evaporation, imperfect sealing it is there, interaction of the liquid with the sample or maybe substrate is there, so that you can have long-term stability issue. So to overcome this one, we thought to work on completely solid state device called as a sandwich type of the device, called a symmetric type of the device, where 2 electrodes of the same type. If you are using 2 electrodes of the different type, then you can say it is asymmetric type of the supercapacitor. So this way device contributes as solid state symmetric device. Here you can see that vanadium oxide coated on the carbon nanotube. So gray color it is there, stainless steel, black color it is there, carbon nanotube, green color it is there, vanadium oxide coated on the carbon nanotube. And these 2 electrodes as symmetric type, same type. In between, we have embedded lithium, that is lithium LiClO4 embedded inside the PVA. So PVA, it is a non-conducting, and lithium ions are conducting. Means lithium ions are conducting ions embedded inside the PVA matrix that we have made the gel. We have penetrated inside this both electrode in between, sandwiched together. We have pressed that one for overnight with certain load pressure which is applied normal to the substrate, and we made this device which is completely liquid free, called as a solid state device, having the area, for example, here 3 by 4 centimeters square. And here at the last image, you can say it is possible to bend this type of this device. There is no perfect sealing, just we have made tissue tape at the edges so that you can bend this type of the this type of the supercapacitor. So whenever we are making this type of the symmetric device, we obtain the potential window, we optimize that one, which is about 1.5 volt. It gives about 1.8 volt, and the specific capacitance we observed it is 468 farad per gram at 2 millivolt per second. And beauty is that this device gives better stability than the electrode. It is about 96% stability it is there for 4,000 cycles. Not only this one, we have carried out the GCD as well as energy density, power density calculation, and we observed about 72 watt hour per kg, consuming power up to 0.3 kilowatt hour per kg. Not only this one, as we are saying it is a flexible, we have tested with respect to the bending angle. And we have tested up to 175 degree of the bending angle. It is almost stable up to 90%. And also we have tested for almost continuous 7 days. So it is almost 7 days, it is stable. And this is the VN90 panel. You can see 3 by 4 centimeter device it is there. We have used to run this VN90 panel consisting of 21 red LEDs. So here you can see that this device it is charged and it can run up to 6 minutes. And this result it was published inside the Nature Scientific Report. Just vanadium oxide coated on the stainless steel, it was published inside the Electrochemical Acta, and vanadium oxide which was coated on the carbon nanotube, which was published inside the Nature Scientific Report. And this video that I am going to show you, that is also available on this Nature Scientific Report website. Here you can see that this is now device. It is charging. This is 3-volt battery we have used. This is completely solid state device, 3 by 4 centimeters square. Video is visible, sir.
Yes, sir. Yes, sir. It's visible.
Okay. Yeah, now it is charged. Now you can see that we have run this one VN90 panel through this charged, completely solid state, flexible supercapacitor consisting of 21 red LEDs. Now you can see that this VN90 panel run up. This can run up to 5 to 6 minutes. And here you can see that without any sophisticated instrumentation that we have developed this device in the laboratory, which is a working model of this one VN90 panel. So here you can get the idea how this low-cost chemical method can be used to make the device like a solar cell, like a supercapacitor. This is another one model that I wish to demonstrate, that this is small fan we are used to run this one. This is charging. This is two-way key. And this work, it was carried out under the Technology Mission Division project from DST. I, as a PI, then CIMET, Dr. Kale, he was co-PI, one industry partner, Scale Technologies, they are collaborating for this project. And here you can see that this fan is running. So for the short charging also, it is running very well. And this VN90 panel, which is running, it is already uploaded on the scientific report journal. And this fan we have demonstrated in the one DST meeting. DST, they have invited me to give this presentation, and they have given one booth. And here you can see that VK Saraswati, member Niti Aayog, they have visited our booth, and this Professor Ashutosh Sharma, Ji, Secretary DST, and Professor Rao, who was director of IIT Delhi, they have visited and they have appreciated our work. Not only this one, just one project I'm presently running from the DA Bareness, and our one project collaborator, Dr. Rath, he was providing tin oxide sample, and we have made this large scale device 4 by 10 centimeters square, and we use this one to run this small fan. Here you can see that. And not only this, this is a big panel we did with having LEDs more than 800, and this LED panel having more than 800 LEDs, we are run up with this type of the solid state supercapacitor, which is tin oxide based. And here you can see that it requires very large current, as more than 800 LEDs are there. You can see that. But it can run for a short time, as it requires very large current. So this is National Institute of Technology with my laboratory name. So these are the project, 7 projects completed and 3 are running. At this one, just I am telling about this tin oxide from the DA Bareness that we have used to run up this big panel. Not only this one, we got a grant of 2.47 crore. These are the 70 students, they have completed this one. a PhD under my guidance, and they are some are working abroad, some they have worked abroad. And just last year, my PhD student, Dr. Vidhan Pandit, he got Marie Curie Fellowship, and he is working in UK along with collaboration from MIT USA. And two of my students, they got enlisted in top 2% scientists. My PhD guide also got in top 2%, and his guide also got to top 2%. And here you can see fourth generation. It is there. PhD students guides relationship along with top 2% listed. One book, it was published in the Springer, contains 13 chapters with 12 chapters devoted to thin film techniques and how it can be utilized for the device grade development like solar cell, supercapacitor, as well as sensor. So these are the different talks I have given, like funding agencies with effective research proposal drafting, aspects of research and review article writing, and many more. So if any questions, please.
Thank you, sir. Thank you so much. It was really very thought-provoking and brainstorming session. It was really very interesting to see some working models live, the demonstration of energy devices, energy storage devices, and all. Thank you so much. Now the session is open for questions. If anyone is having question, you can please ask to sir.
Or here my phone number is also given. If they have any queries or something also, they can write me email.
Yes, any questions?
Hello. Hello.
Yes. Yes, please.
Sir, the supercapacitor can be give the capacity as compared to battery.
Not we can say capacity, we have to increase the energy density. Energy density should be comparable to the battery. We have to increase the energy density of the supercapacitor, which can be comparable to the battery. Then it is possible to replace the battery with type of the supercapacitor.
Okay.
Sir, I want to ask, batteries are like not recyclable. Nowadays, batteries are also coming in recyclable mode, but these capacitors are recyclable or not?
Yes, these are also recyclable, but we have to, whatever the material it is there, that material we have to recycle and use it again. So, for example, now we are doing some batteries. Also, just one paper we have submitted, recycled battery, and that material we have used for supercapacitor.
Right. Okay, sir. Yes, any question? Okay, so then I consider that no questions anymore. And on this platform of March 2024, I would like to thank to Dr. Sanpal sir for his valuable time, insightful talk, and all the guidance on the supercapacitors. And thank you, sir, for being with us. Thank you, sir. Thank you so much. And I would like to thank all participants also for joining us and being with us. Thank you. Thank you, sir. So with your all due permission, I would like to end the session here.
Okay.
Thank you so
Can I
much.
leave now?
Thank you all.
Yeah, thanks.
So myself, Dr. Shruti Patle.
Okay. Can I leave now?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Okay.
You can leave.
Yeah, thank
I'm
you.
ending the session. Yes. Thank you so
Thank
much.
you.
Thank you. Thank you.
So very good afternoon. Good afternoon, you have two participants in your conference and who can't speak or read, but they have done back some poster and oral presentation. Dr. Roxana Rada. She has presented the question and the winner of the Best Question Award. I request Dr. to give. Simona Rada. I invite Professor Simona and Dr. Nilesh to please answer. Okay, Shekhar, please. So what is the participation
The research. Yes, come, sir, आइए ना. आप सर आप लोग आइए हम साइड पे आ जाए. आइए ना. अच्छा ठीक है. Yes, really, with you. All please, all are requested to join us. All participant delegates, please come and join us. This is final board, yes. Final
Lunch, after lunch, there will be validation.
There is more. Thank you.
Lunch. Move for the lunch after the
Moving to Nagpur, just no. Please.
ये वो गाड़ी वाले को बता दो लोटी करना आप चलिए एक आप पीछे ले जाएंगे
Ma'am, excuse me. They want food. अरे नहीं आप कुछ फोटो एक्सक्लूसिव रहने दीजिए है ना ये सब तो हाँ ये मैं भी बता मैंने एक्सक्लूसिव है one click one sir आप आइए please आपके मैम one yeah we had okay WhatsApp. No mail ID. I don't know which things are. So we can. Hello, right? Yeah, you can. Then right, because we belong to a different college. That's the